Hello students, today we are going to discuss oxidation of lipids. So first, what is lipids? Lipids are quite different from carbohydrates and proteins, as carbohydrates are the polymers of the monosaccharides and proteins are the polymers of the nucleic acids and pyrimidine and amino acids. Whereas lipids are not true polymers. This is the combination of heterogeneous substances which have common properties, hence they are kept in a one class. And fatty acids are the components of the lipids. So before oxidation, let's have a look on the fatty acids. Fatty acids we get in our body from the dietary components of carbohydrates, amino acids. If we consume them in excess, they are converted into the fatty acids and stored in our body in the form of triglycerols. De novo means the new synthesis of the fatty acids occurs in liver, kidney, adipose tissues and lactating mammary glands. Fatty acids production is located in the cytosomal fractions of the cell. Fatty acids are synthesized by acetyl coenzyme A and degraded to acetyl coenzyme A. So their synthesis and their degradation is a common fate. But synthesis occurs in the cytosol of the mitochondria, whereas degradation occurs in the mitochondria, cytosol of the cell, and degradation occurs in the mitochondria. So this is the basic difference between the degradation and synthesis of the fatty acids. Fatty acids usually exist in our body in the form of triglycerols, that is TAG, and when they are released in our blood, they are known as free fatty acids. Free fatty acids, they released into the blood circulation. They bind with protein, that is albumin, released from our liver and carried out with albumin for the fuel to get the energy. However, brain, erythrocytes and adrenal medulla, they cannot utilize fatty acids for the energy requirement because they do not have the mitochondria. 95% of the energy we obtain from the oxidation of fatty acids. Hence, the synthesis of the fatty acid is essential for our body and to get the energy. And that occurs due to the process by the process of oxidation. Now, what is the source of carbon? Acetyl coenzyme A is the source of carbon atoms, whereas NADPH and FADH they provide the reducing equivalents, and ATP is being supplied for the fatty acid formation. Now, beta oxidation. First, why we used to call it beta oxidation? As the fatty acid molecules, they have so many carbon atoms and a carboxylic group as a functional group. So the first carbon atom which combines with the functional group is known as alpha carbon atom, whereas the second carbon atom is named as beta and third one is gamma and so on in alphabetically number. Because maximum oxidation of the fatty molecules occurs at beta carbon atom, hence it is known as beta oxidation. This results in the sequential removal of a two carbon segments, that is acetyl coenzyme A, means the oxidation occurs of the long chain fatty acids and break down into the two carbon atom, that is acetyl coenzyme A. This process involves three steps. First is activation of fatty acids in the cytosol. Second is transport of fatty acids into the mitochondria. And third one is beta oxidation proper in the mitochondrial matrix. Now first step, that is activation of acetyl coenzyme A. Here I have given the formula of acetic acid, that is CH3COH, and this is acetyl coenzyme A. CH3, this is the coenzyme A. So how acetyl coenzyme A is being activated. This is the formula of fatty acids, carbon atoms, and this is the carboxylic group. By the breakdown of one ATP molecules and release of the two high energy phosphate molecules in presence of an enzyme, thiokinase, this fatty acids is being converted into acyl adenylate. where coenzyme replaced the AMP molecules and it converted into the active acyl coenzyme A. Now this active acyl coenzyme A is ready to enter inside the mitochondrial matrix. The second step is transport of fatty acids to the mitochondria. Here one thing is to be noted that the fatty acids which have 1 to 10 carbon atoms, they are simply diffused into the mitochondria because they are small chain fatty acids and plasma membranes allow them to enter inside the matrix. But the fatty acids which are of longer chain, 12 to 20 carbon atoms, they can't enter inside the plasma membrane of mitochondria. They don't allow it. Whereas the carbon atoms, fatty acids having more than 20 carbon atoms, they all metabolize in peroxisomes. Now we are talking about the medium chain of carbon atom of fatty acids, that is 12 to 20, that is palmitoyl acid and stearic acids. So they have the odd or even carbon atoms in between 12 to 20. So let's have a look on the carnitine shuttle. We used to call it carnitine shuttle. What is carnitine shuttle? The long chain fatty acids, they combine with a protein molecule, that is carnitine. Here is the carnitine capture, that is translocase 1, and it makes acyl carnitine compound which enters through membrane inside the matrix of the mitochondria, and where it is again being break down by the carnitine translocase second and into the acetyl coenzyme A and carnitine. So carnitine from here goes back to the cytoplasm of the mitochondria of the cell, whereas acetyl coenzyme A enters into the beta oxidation. So now the third step is, that is final beta oxidation. I have given a key to this beta oxidation, that is OHOC. O is oxidation. It involves the four process: oxidation, hydration, oxidation, and final is the cleavage. So have a look over here. Each cycle of beta oxidation liberating a 2 carbon atom unit, that is acetyl coenzyme A in the last. Now first step is oxidation. Come here. So this fatty acyl coenzyme A, it dehydrogenation occurs by the presence of FADH, FAD to FADH2 in presence of acyl coenzyme A dehydrogenase. As a result of which, double bond is formed between alpha and beta carbon atom over here. Alpha and beta double bond is formed. And in the presence of acyl coenzyme A hydratase, the next process is hydration. During the hydration, one OH molecule is attached to the beta carbon atom, whereas H molecule attached to the alpha carbon atom. And now it becomes beta hydroxy acetyl coenzyme A. Now the next process is hydration. The enol brings out the hydration and it becomes beta hydroxy acyl coenzyme A. Now the third is again oxidation. Oxidation, hydration, oxidation and cleavage. Now the third step is oxidation. Beta hydroxy acyl coenzyme dehydrogenase, it catalyzes the second oxidation and generates NADH. And it generates NADH. This product forms the beta ketoacyl coenzyme A. And now here the breakdown occurs between these two alpha and beta carbon atoms. And 2 carbon atom molecules are formed. The fourth step, that is cleavage, that is cutting off this molecule of beta ketoacyl coenzyme A into the 2 carbon atom molecules. One is acetyl coenzyme A in presence of an enzyme, that is thiolase or the thiokinase, and another is fatty acyl coenzyme A. So now this beta carbon atom, the compound having beta carbon atom and coenzyme A, is ready to enter into the next TCA cycle. So this is beta oxidation. Now we are coming to the energetics of the beta oxidation. As you know that fatty acids, they may be the odd and even carbon atoms. There may be the 18, there may be the 16, there may be the 14 and so on. So their energetics are different. It's based on the number of the carbon atoms. What is the rule for this, for the energetics? Number of acetyl coenzyme A, if suppose if it is 16, then the number of the cycles will be, the number of the production of the acetyl coenzyme A will be n divided by 2. That is the number of the carbon atoms divided by 2. So there will be 8 acetyl coenzyme A molecules will form in case of C16, that is palmitoyl acid, fatty acids. And how many cycles will occur? 7 cycles will occur. So n divided by 2 subtracted minus 1. So with the help of 7 cycles, 8 molecules of acetyl coenzyme A is formed. And this acetyl coenzyme A then enters into the TCA cycles and it generates 10 ATP molecules. Now look over here at the energetics of beta oxidation. Beta oxidation, as in case of palmitic acid, what will happen? 7 cycles will occur and 7 NADH will form, and each NADH gives 2.5 ATP molecules. Now here the question arises, you will ask that why not 3? Because till now you are reading that NADH giving 3 ATPs and FADH give 2 ATPs. So the logic behind that is that during the electron transport chain, NADH, it is an oxygen acceptor, and total 10 protons are being transported from matrix to inner mitochondrial membrane. 4 protons via the complex 1, 4 via complex 3 and 2 protons via complex 4. And to make 1 ATP, 4 protons move from inner mitochondrial membrane to matrix via ATPase. So thus NADH, it have 10 hydrogen molecules. So 10 divided by 4, it will come 2.5. And how many NADH molecules were produced? 7. So 2.5 multiplied by 7, it will come 17.5. And similarly in case of FADH2, 7 molecules are being formed, and because it pumped out 6 hydrogen molecules, hence 6 divided by 4 will come 1.5, and 1.5 multiplied by 7, so 10.5. Now all, as I have told you, that if it has the 16 carbon atoms, so 8 acetyl coenzyme A group molecules will be formed, and each generating 10 ATP molecules. So 8 multiplied by 10 will come 80. So the total energy from one molecule of palmitic acid is 108 ATPs will be generated. And during this process, 2 molecules of ATP are being consumed, as ATP molecules is being converted into AMP in a activation of acetyl coenzyme A. So net gain in the ATP oxidation of one molecule of a palmitic acid will be 106, and this energetics will depend on the number of carbon atoms. So that's all about the beta oxidation. Hope you will understand the yield of energetics and what is beta oxidation. Thank you.